Good morning, students. Once again, welcome back to session 5 of Banach spaces classes. So, in the last class, we have studied words meant by an bounded linear transformation and a continuous linear transformation on Banach spaces. Say the transformation T is said to be T from Banach space, say x to Banach space y is said to be bounded if norm of T of x is less than or equal to some k times into norm of x. This holds for every x in x. So this is the definition. So then say if the same transformation T from x to y is linear, where x and y are Banach spaces, then when do T inverse exist and when it will be continuous. So if T from x to y is linear, then T inverse exists and continuous on its domain of definition. What is the domain of definition of T inverse? T inverse is T of x is the domain of definition. Okay, so it is continuous on its domain of definition and T inverse exists and continuous. T inverse is continuous means what? What is the condition? So that condition we will prove it now. M times into norm of x is less than or equal to norm of T of x for every x belongs to x. Generally, T inverse is said to be continuous means every you know that continuity continuity implies boundedness and boundedness implies continuous. So in the words, so to show T inverse is bounded or continuous means T inverse of say y is less than or equal to some m times into norm of y for every y belongs to where? T of x. This is the domain of T inverse, right? This is the definition. Actually, we have to show this is T inverse of T inverse. The mapping T inverse is bounded if this condition. Now, say so we have a theorem. Say T from x to y is linear. Then T inverse exists and is continuous on its domain of definition T of x if and only if there exists a constant m such that m times into norm of x is less than or equal to norm of T of x. Okay, so this happens if and only if T from x to y is linear, then T inverse exists and is continuous on its domain of definition if and only if this condition holds true. Okay, so first suppose the condition, given condition, say m into norm of x less than or equal to norm of T of x for every x belongs to x. You call this as 1. Suppose this holds. This is true. So what we have to show? T inverse exists and is continuous. T inverse exists and is continuous. Now T inverse exists. When T inverse exists? T inverse exists if and only if T inverse exists. If and only if T is 1 to 1. T is 1 to 1 because the mapping which we have taken from x into y, not x onto y. So x into y, so therefore definitely the mapping is a into mapping. So to show it is T inverse exists, we need to show T is 1 to 1. If T is 1 to 1, definitely T inverse exists on its domain of definition, right? So for this you take any 2 points, say x1 comma x2 belongs to x, x1 comma x2 belongs to x, then consider T of x1 is equal to T of x2. T of x1 is equal to T of x2 implies what? T of, say directly I will write x1 minus T of x2 is equal to 0. This implies since T is a linear mapping, T of x1 minus x2 is equal to 0. This implies T of x1 minus x2 is equal to 0 implies x1 minus x2 is equal to 0. This happens implies x1 is equal to x2. Therefore, the mapping T is 1, 1. Therefore, the mapping T is 1, 1. Therefore, if the mapping T is 1, 1, then T inverse exists. Now, we need to show T inverse exists. And so, if T inverse exists, then what will happen? If T inverse exists means there is a mapping T inverse from the domain of T of x to x. So, therefore, to each y in the domain of T inverse, what is the domain of T inverse? So domain of T inverse is T of x. So to each y belongs to T of x, y belongs to domain of T inverse, there exists x belongs to x, x belongs to x such that T of x is equal to y. T of x is equal to y happens if and only if T inverse of y is equal to x. So T inverse exists means to each y belongs to the domain of T inverse. Domain of T inverse is T of x. There exists x belongs to x such that T of x is equal to y. This happens if and only if T inverse of y is equal to x. You call this as number, say 2. You call this number 2. Then say 1 is equivalent to the equation 1, which we call it as denoted by m times into norm of x less than or equal to norm of t, becomes, what will happen for this? So this is m times into norm of T inverse is norm of x is T inverse of y less than or equal to norm of y. This implies norm of T inverse of y is less than or equal to, say this is m times into here. This is 1 by m times norm of T inverse of y is less than or equal to m 1 by times m into norm of y. So 1 by times m is greater than 0 means 1 by m exists. So that I may denote it by big M, where big M is equal to 1 by m. Then what will happen? Norm of T inverse of y is less than or equal to, norm of T inverse of y is equal to n times into norm of y. What you can say now? Norm of T inverse of y less than or equal to m times norm of y means, by definition of inverse of a bounded of a mapping, T inverse of y is bounded. T inverse of y is bounded means T inverse is continuous. Thus we have assumed that m times into norm of x is less than or equal to norm of T of x, and we have shown that T inverse is continuous or bounded. Okay, one way we have proved. Conversely, we assume that T inverse exists and is continuous on its domain of definition. Then we will show the condition is 1 holds true. Okay, say you assume T inverse exists. And continuous on its domain of definition, and continuous on T of x. The domain of definition is T of x. Say let x belongs to x be arbitrary. What will happen? Since T inverse exists, there exists, if x belongs to x, what will happen? There exists y belongs to T of x such that T inverse of y is x. This happens if and only if T of x is equal to y. And since T inverse is continuous, it is bounded. Therefore, by again we take T inverse is bounded means T inverse of y is less than or equal to k times into norm of y for every y belongs to T of x. Right. So this implies, again we use the same condition as above. So norm of x is less than or equal to k times into norm of y. Y means T of x. So this implies 1 by k times into norm of x is less than or equal to norm of T of x. 1 by k times into norm of x is less than or equal to T of x. So 1 by k I can take it as some m times into m into norm of x is less than or equal to norm of T of x. Therefore, this is the one which is proved, which is 1. Okay. So we have proved that if T from x to y is a mapping, then T inverse exists on its domain of definition. T inverse exists and is continuous on its domain of definition if and only if this condition holds true. So in future, whenever we are going to show T inverse continuous means no need to prove the condition of this condition. Okay, it is enough to show that this condition. Okay, so from these two, and also you know that when t is bounded means norm of t of x is less than or equal to k times into norm of x, or say big M times into norm of x for every x belongs to x. So from these two, from the definition of t to be continuous and from definition of t inverse to be continuous, we can say the mapping t from x to y. Suppose if you have a t from the Banach space x to the Banach space y, then t and t inverse exist and are continuous. Both t and exist, t inverse also exists and continuous if and only if what will happen? You join both the statements. If and only if there exist m positive and big M positive such that m times into norm of x is less than or equal to norm of t of x less than or equal to big M times norm of x. So this is the condition for t to be continuous or bounded, and this is the condition for t inverse to be continuous and bounded. Therefore, say with the mapping t from x to y is said to be continuous or bounded if and only if t and t inverse are continuous and bounded if and only if there exist constants m and m such that m times into norm of x is less than or equal to norm of t of x, which is less than or equal to m times into norm of x. So when t and t inverse are continuous, then what we say, the mapping t is a homeomorphism. The mapping t is a homeomorphism means the mapping t from x to y is homeomorphism if and only if this condition holds true. This is also a very important result. Okay. Now let's come to another definition. Suppose t is a mapping from the norm-linear space x to the norm-linear space y. Then we can define the norm of t, norm of the mapping t to be. How do you define the norm of t? This is supremum of norm of t of x, where x belongs to x, norm of x is less than or equal to 1. So this can be stated as t from x to y is a mapping linear transformation. Okay, t from x to y is a linear transformation. Then norm of t is supremum of norm of t of x, the values, such that x belongs to x, norm of x is less than or equal to 1. This norm usually known as operator norm on x, operator norm, or this is the standard norm on defined on x. Okay. So now say we can show that this norm, this is actually standard norm. So this norm will be equivalent to many norms that we can show it now. Say the above norm may be equal. This is equivalent to supremum of norm of t of x, such that x belongs to x, norm of x is equal to 1. Okay, this is equal to supremum of norm of t of x, where say look here, supremum of this is equal to supremum of norm of t of x, so where x belongs to x, norm of x is equal to 1. That I will denote it by a. And the other norm, same norm is supremum of norm of t of x by norm of x, where x belongs to x, x is non-zero. And the third one is C, I call it as infimum of all those values of k, where k is non-negative and norm of t of x is less than or equal to k times norm of x for every x belongs to x. Means the norm which we define, norm of t is equal to supremum of norm of t of x, where x belongs to x, norm of x is less than or equal to 1, may be taken as any of these norms. So in the coming theorems, say we use whenever we required. So instead of considering this norm, this one, I may consider one of the above norms. So, and we have in this, actually this is considered as one theorem, and the proof is given. That proof is very simple. You can follow it up. That I will provide it in the study material. Okay. Now let's come back to one of the important theorem of this session. So suppose x and y. Let x and y be any two non-linear spaces, and let B of xy denote the set of all bounded or continuous, one and the same set of all bounded or continuous linear transformations from x into y. So B of xy denotes the set of all bounded continuous linear transformations from x into y. So this is like, say, in group theory you have studied what is meant by homomorphism of say this is or in vector spaces. In vector spaces, home of VW. What is home of VW contains? Homomorphism of VW contains set of all homomorphisms from V into W. This is like home of VW itself. Instead of here one addition condition is there. Homomorphism here means only linearity condition. Homomorphism condition is nothing but the linearity condition. But here the additional condition is those maps are bounded or continuous. The same. So this is denoted by B of xy, or in other words, if we written it in a set notation, B of xy is equal to set of all transformation T such that T from x to y is linear and continuous, or linear and bounded. So B of xy contains set of all transformation T from x to y which are linear and continuous. So now the question is here, so can we make this B of xy as a, there we have shown that home of VW is a vector space. You know how to prove home of VW is a vector space. You have all done this. Okay. Now, can we make B of xy as a Banach space here? Banach space means before that we need to make, can we make B of xy as a non-linear space? See here, B of xy contains not the ordinary terms. They are all functions or the maps from T from x to y which are continuous as well as which are linear. Now can we make B of xy as a non-linear space? Yes, we can make B of xy as a non-linear space by suitably defining the operations or the norms. First, can B of xy is a linear space? Non-linear space means it must be a linear space. Can B of xy is a linear space? Yes, B of xy is a linear space. Why? Because B of xy is nothing but only bounded. Additional condition is the additional condition is the boundedness. Linearity already there. Already we have shown that the transformations from, say, if we take some S as the set of all transformations, S is equal to set of all transformations, say from x to y, set of all linear transformation from x to y. If I take, definitely B is a subset of S. B is a subset of S. Is it true? Yes, B is definitely a subset of the set of all transformations from x into y. Okay. In order to show that B of xy is a linear space means it's a vector space. So how to show? We need to show every every condition of a vector space. Instead of that, can we show B is a subspace of the vector space? You already know it. The set of all the vector space of all transformations from x to y, or in other words, this is nothing but home of xy. This is a vector space, you know that. So if I show B is a subspace of this, then then it implies that B of xy is a linear space. So before that we need to define the operations, already you know it. What are the operations? Say if t1 comma t2 is any two elements of b of xy, then so you know how to add and how to introduce the vector addition and scalar multiplication, and alpha is a scalar belongs to the field f. Then t1 plus t2 of x is, what are the operations? Vector addition is t1 of x plus t2 of x, one condition vector addition. The other is alpha into t1 of x is alpha times t1 of x. These are the standard two operations that you can define it on b of xy, right? So now we are telling that we will show that b of xy is a subspace of home of xy, or it is the set of all linear transformation from x to y. So for this, subspace means what? You take any two elements, say t1 comma t2 belongs to b of xy, t1 t2 belongs to t of xy, you take. Then alpha comma beta, you take any to be any scalars. F means it is understood that they are the scalars. Now t1 t2 belongs to b of xy, and this one means what you have to show? Alpha into t1 plus beta into t2 belongs to b of xy, then only it will be a subspace. This is the standard condition, you know it. So if for every two elements t1 comma t2 belongs to b of xy, alpha comma beta belongs to f, alpha t1 plus beta t2 belongs to b of xy. This is the standard condition. So how to prove this? Now t1 t2 belongs to b of xy means they are bounded linear transformations. Therefore norm of, what will happen? Norm of t1 of x is less than or equal to, say, some constant, say k1 times norm of x, and also t2 is bounded, or bounded means norm of t2 of x is less than or equal to k2 times into norm of x. This holds for every x belongs to x. Now you consider the norm of alpha t1, say norm of alpha into t1 plus beta into t2 of x, alpha into t1 plus beta into t2 of x. So this is equal to norm of alpha into t1 into t2 of x is alpha into t1 of x plus beta into t2 of x. So this is equal to, directly I will write alpha into t1 of x plus beta into t2 of x. So use the triangle unity. This is less than or equal to, this is directly I will write mod of alpha into norm of t1 of x plus mod beta into norm of t2 of x, right? So this is less than or equal to alpha into norm of t1 of x is less than or equal to what? K1 times norm of x plus mod beta into k2 times norm of x. So norm of x is common. This is equal to mod of alpha into k1 plus mod beta into k2 into norm of x. So this is again some constant, say I will denote it by k. Therefore norm of alpha into t1 plus beta into t2 of x is less than or equal to k times into norm of x. Then what you can say? Alpha into t1 plus beta into t2 is bounded. Therefore alpha into t1 plus beta into t2 belongs to b of xy. Therefore b of xy itself is a linear space. Okay, understand this? B of xy is a linear space. Now we need to make b of xy as the non-linear space. So b of xy is a non-linear space means, so I need to prove all the conditions of a norm. It takes little time. Say what is the norm? I can define it on t of b of xy. So this is the standard norm. I will take norm of t is equal to supremum of norm of t of x such that x belongs to x, norm of x is less than or equal to 1. So norm of t is equal to supremum of norm of t of x such that x belongs to x, norm of x is less than or equal to 1. So we need to prove this is a norm on b of xy, so that b of xy becomes a non-linear space. Let's look at each of the conditions. The first condition is norm of t must be greater than or equal to 0. So now you know that. I will show it and explain. Okay. So as norm of t of x is always non-negative because t of x is a vector in y. So norm of t of x definitely greater than or equal to 0 for every x belongs to x. If this happens, then what will happen? Norm of t of x is greater than or equal to 0 means they are non-negative terms, means supremum of non-negative terms is also non-negative. I will take supremum of norm of t of x such that x belongs to x, norm of x is less than or equal to 1, is greater than or equal to 0. This is nothing but what? Norm of t. So therefore norm of t is greater than or equal to 0. So this is the condition 1. So next, suppose norm of t is 0. Norm of t is 0 happens if and only if supremum of norm of t of x, where x belongs to x, norm of x is less than or equal to 1. This is the norm of t is equal to 0. So this is equal to supremum of norm of t of x by norm of x. Second condition, that equivalent norms I taken such that x belongs to x, x is not equal to 0 is 0. So this happens if and only if norm of t of x by x. Supremum of this term, this set is 0 implies each of the terms must be 0. Each of the terms are norm of t of x by norm of x is 0 for every x belongs to x, x is non-zero. So this happens if and only if this by this is 0 but norm of x is not 0 means what? The only possibility is norm of t of x is equal to 0 for every x belongs to x. So norm of t of x is 0 means, since norm is by definition of a norm, so t of x itself is 0 for every x belongs to x. Therefore t of x is 0 means t carries every element to 0 means that is nothing but a 0 transformation. So we have assumed that norm of t is 0 and we have shown that t is equal to 0. Okay. So second condition we have proved. Let's pick up the third one. Third condition is what? So we have taken t1 t2 belongs to b of xy. So I consider norm of t1 plus t2. So this is very simple. Supremum of norm of t1 plus t2 of x, where x belongs to x, norm of x is less than or equal to 1. This is the standard thing. So I just use the linearity condition. Okay. So we arrive at supremum of norm of t1 of x, where x belongs to x, norm of x is less than or equal to 1, plus supremum of norm of t2 of x, where x belongs to x, norm of x is less than or equal to 1. So this is nothing but this is equal to norm of t1 plus norm of t2. Therefore norm of t1 plus norm of t2 is less than or equal to norm of t1 plus norm of t2. So the fourth condition is, the last condition is, if alpha is any scalar, then norm of alpha t is what is supremum of norm of alpha into t of x, where x belongs to x, norm of x is less than or equal to 1. So you can take mod of alpha outside, supremum of t of x, that is equal to mod of alpha into norm of t. Therefore the norm which we define is a norm on, which is defined is a norm on b of xy, and so b of xy becomes a norm linear space. First we have shown it is a linear space, now it is norm is the defining norm is the condition. This is a norm on, this is a norm on, this is a norm on b of xy. Okay. Therefore b of xy becomes a linear space. So this is one part of the proof. Now so the second part is, I asked, when do b of xy becomes a Banach space? Means do b of xy is complete? Yes, b of xy is complete. Only restriction is if y is complete. If y is complete, then b of xy is also complete. Okay. So this is a hard part of the proof here. Suppose y is complete, I'll take. Y is complete. So, and I need to show b of xy is complete. For that, I taken some Cauchy sequence in b of xy and let Tn be any Cauchy sequence in b of xy. So Cauchy sequence means what will happen? Norm of Tn minus Tm tends to 0 as m and n tending to infinity. You call this as number 1. Call this as number 1. Now for each x in x, we have norm of Tn of x minus Tm of x. This is equal to Tn minus Tm of x. We can definitely write like this, less than or equal to norm of Tn minus Tm, that's into norm of x. We can write. So this type of condition we have proved already. So now this implies this tends to 0 as m and n tend to infinity by 1. Therefore what you can say, norm of Tn of x minus Tm of x is tends to 0 as m and n tending to infinity means what? Tn of x becomes a Cauchy sequence. Where Tn of x lies? Tn of x lies in y, therefore it is a Cauchy sequence in phi for each x belongs to x. Now we have assumed that y is a complete space. Y is complete means there exists some a vector, say t of x in y, such that Tn of x converges to t of x. Now Tn of x converges to some mapping t of x in y means, so this gives the existence of some transformation t. Okay, thus we define the mapping t from t of x into y. We have a existence of the mapping t. Now can this t belongs to b of x phi? The condition is, although Tn of x converges to t of x, so we have we can define the mapping. We have seen the mapping t exists, but whether t is bounded and linear and continuous, so then only t belongs to b of x phi. So I will check this whether t is linear. Yes, let t x y belongs to x and alpha beta be scalars. Then t of alpha x plus beta y. T of alpha x plus beta y is equal to what? Limit n tends to infinity. This is t of x is the nothing but the limiting value of Tn of x. So this is equal to limit n tends to infinity Tn of alpha x plus beta y. So this is equal to alpha times limit n tends to infinity Tn of x plus beta into limit n tends to infinity Tn of y. Alpha into limit n tends to Tn of x is t of x and limit n tends to infinity Tn of y is t of y. Therefore alpha into t of x plus beta into t of y. Thus t of alpha x plus beta y is alpha times t of x plus beta times t of y. Therefore we can say t is linear. Now the second condition is whether t is bounded or continuous. So we have norm of t of x is equal to norm of limit n tends to infinity Tn of x, that's equal to limit of norm of Tn of x less than or equal to. So I can replace limit by the supremum. Definitely this is limiting value is less than or equal to supremum value or less than this, equal to this. So less than or equal to supremum of norm of Tn into norm of x. So supremum applies for this only because n term is there here. Less than or equal to supremum of Tn into norm of x. Less than or equal to Tn into norm of x. But we know the condition that, so you already proved in the beginning of the session 1 class itself, in session 1, mod of norm of x minus y is less than or equal to norm of x minus 1. And so here norm of Tm minus norm of Tn is definitely less than or equal to norm of Tm minus Tn, which tends to 0 as m tends to infinity, you know, from 1. So therefore norm of Tn is a Cauchy sequence of real numbers. Norm of Tn, norm of anything is a real number. So Cauchy sequence of real numbers and hence convergent and bounded. Therefore convergent means, so there exists a constant k positive such that supremum of norm of Tn is less than or equal to k, because I assume the condition that it is bounded. So supremum of norm of Tn is less than or equal to k. You call this as number 3. So from 2 and 3 we have 2 is what? 2 is norm of t of x is less than or equal to supremum of norm of Tn less than or equal to x. Okay, this is 2. So now using 3 here, what will happen? So from 2 and 3 norm of t of x is less than or equal to supremum of norm of Tn is value is less than or equal to k, less than or k into norm of x. This implies t is bounded. Now t is linear as well as t is bounded, therefore t is an element of b of xy. Okay, t is an element of b of xy. The final thing is, so the Cauchy, we need to show the sequence which you are consider in b of xy Tn converges to t. Okay, there are a lot of steps in proving this. Okay, so for this let epsilon be positive given. Since Tn is a Cauchy sequence, there exists say constant m naught such that m comma n greater than or equal to m naught imply what will happen by definition? Norm of Tm minus Tn is less than epsilon by 4. So in one condition 1 also I taken norm of Tm minus Tn tends to 0 as m tending to infinity. So the same thing can be redefined as there exists some constant m greater than 0 such that m comma n greater than or equal to m naught imply norm of Tm minus Tn is less than epsilon by 2. You call this number 4. Next let x belongs to x be such that norm of x is less than or equal to 1. Definitely we have a vectors in x the space x such that this condition holds true. Okay, then as Tn of x tends to T of x, we have proved, we can choose a positive integer mx, we can choose a positive integer mx greater than m naught chosen such that norm of Tmx of x minus T of x, norm of Tm of x minus T of x is less than or equal to epsilon by 2. So means what will happen, Tn of x converges to T of x means norm of T of x, norm of, what will happen, norm of Tn of x minus T of x is less than or equal to epsilon by 2 for every n greater than or equal to mx anta ತಗೊಂಡ್ಬೋದಾಯ್ತು. So or in the words, norm of Tmx of x minus T of x is less than or equal to epsilon by 2. You call this as number 5. Therefore, what will happen finally, therefore for all n greater than or equal to m naught, for all n greater than or equal to m naught and all x such that norm of x is less than or equal to 1, we have norm of Tn of x minus T of x. So this is equal to Tn of x minus Tmx of x plus Tmx of x. Add and subtract Tmx of x minus T of x. So this is equal to, so here only thing is why written Tm of x means, so the integer corresponding to x only. Okay, so that we return. So I group the terms and apply the second triangle inequality. We can see that norm of less than or norm of Tn minus Tm of x, because norm of x is what? Because norm of x we have taken to be less than or equal to 1. Therefore, I return less than or equal to this 1 plus Tm of x minus T of x, I return as it is. Okay, Tm of x. Then what will happen? Say this is norm of Tn minus Tm of x plus this one. Okay, this is less than Tn minus Tm of x is less than epsilon by 2 plus Tmx of x minus T of x is also less than epsilon by 2, which is less than epsilon by the conditions 4 and 5. So norm of Tn of x minus T of x is less than epsilon means supremum of all these values is also less than epsilon. Therefore, supremum of norm of Tn of x minus T of x, where x belongs to x, and the condition we have taken is for those vectors which are whose norm is less than 1, less than or equal to 1. So x belongs to x, norm of x is less than or equal to 1 is certainly less than epsilon for every n greater than or equal to m naught. This is very important. Okay, this implies supremum of, okay, norm of, I use the condition Tn minus T, x common I taken outside, x belongs to x, norm of x is less than or equal to 1 is less than epsilon. So this implies, or supremum of this is less than epsilon means each of the numbers must be less than epsilon, means norm of Tn minus T must be less than epsilon. Okay, for all n greater than or equal to m naught. This implies what? Tn converges to T. Tn converges to T. Now we have taken a Cauchy sequence Tn in B of xy and we have shown that Tn converges to T. Okay, therefore B of xy is complete. Now understand why we have shown T is continuous as well as bounded. So if T doesn't, we don't know, we have the existence of T, but the T existed in B of xy we don't know. That's why we have shown that T is linear as well as bounded. Other words, we don't know Tn may be converged to some T which may not be element in B of xy, so that B of xy is not complete. So it is complete only when the converging point is also element of B of xy. That's why in the beginning itself we have shown T is element of B of xy, or T is linear as well as T is continuous. Okay, so this is one of the important theorem. So here we will discuss that if B of xy denotes the set of all continuous linear transformations from x into y, then B of xy is itself is a norm-linear space, and moreover B of xy is a Banach space, or B of xy is complete if the restriction is if y is complete. Okay, this is the important theorem. Okay, this is enough for this class. Thank you.